Okay, so it is still the holidays, and so a lot of people are actually enjoying the holidays, and so overall the Q&A attendance is on the lower side. I still don't want to throw away the time slot though, because it will eventually become more popular as school actually starts up again. But I still do want to at least have a look at some of the things that people tend to struggle with. And one of the main things here is this idea of how we handle transformations, right? This is typically one of the things where people get taught for the first time. They see that there's about 1,000 different rules that you have to keep track of, and well, that becomes quite difficult. What if instead you only had one rule to deal with? And that's kind of what this sequence of lectures is going to be on, how we can look at transformations with one fundamental process without necessarily having to worry about each individual rule. Now, this will be only really applicable for an introduction to transformations. You will still need to know how to recognize all of those different rules so you can answer questions a lot quicker, but it will help you in the introduction as to why there are what those rules are, and it will help you when it comes to identifying transformations specifically, usually when they are done in a sequence. Okay, so transformation fundamentals. You can apply any transformation using this three-step process. So the way it works is you try to figure out what point am I starting from and what point am I aiming to get to, right? So if you had some point x, y, let's say it was the coordinate 1, 2, and that point exists on a curve, we want to basically take all points from a curve and move them somewhere else. That's fundamentally what transformations are doing. That's what that first step is all about. The next two is pure algebra. Once you have your equation that converts from x to x prime and y to y prime, you're going to rearrange to get that back in terms of just x and y, and then we're going to sub that new x and y into whatever function we started with. So the first type of transformation we're going to look at here is this idea of the dilation. All right, dilations are all about stretching. In fact, it's literally an English language verb. It is to make or become wider. And so if you think about the way that you can stretch a function, you can do it in two different directions. You can stretch either along a y-axis, or you could stretch along the x-axis, right? Either vertically or horizontally. Now you'll find the book will use different terminology. Both of these are accurate. So saying that you're stretching along the y-axis means that your function is running along the y-axis. It's running vertically. From the x-axis is actually the same direction. So if I quickly just draw an axis, there's two ways I could represent a stretch that looks like that. That is going along the y, there's your y, or it's going away from the x. So from the x is an equivalent way that you could express that, and that's the way that's common, at least in the Cambridge book. I can't necessarily say for, oh no, it's Jacaranda as well. That will do from. Point being, dilations are all about stretching, and they can be applied either in the vertical or the horizontal direction. In this one in particular, we're looking at the vertical direction. As far as the point form goes, we're starting at some initial point x, y, and we're transforming that to some new coordinate x, comma, a times y, where a is the dilation factor, right? It's a multiplication of the original point. So how does that look in an equation? How does that look as an equation? Like this. X isn't changing. The new x is identical to the old x, but the y is. The new y is a times the original y. If we then look at the next step, we're just trying to do some algebra here, rearrange in terms of x and y. This is very, very stock standard. X doesn't change because it's already rearranged, but y does. To get y on its own, you'll just divide both sides by a. This is just fundamentals of algebra, really. And then if you're applying that to a function, you're just going to sub those results into your function. So if you have any function, y equals some function of x, then you replace, in this case, the y with this thing, y over a. And you replace the x with this thing, which just so happens to be x. When you rearrange to get y back on its own, as we do for every function that you look at, it looks like a multiplication of the entire function. So that's why a dilation along the y looks like a multiplication of the function. when you go through these 3 steps, it arrives at that spot. If a is greater than 1, so if a is getting larger and larger, we observe it to stretch further and further along the y-axis. If it's between 0 and 1, we actually see it shrinking along the y-axis. So if you look at an example of how you would apply that to a function, my example here is just the square root of x, right? And I want to apply a dilation factor of 2 from the x. Okay, well, from the x is the same thing as along the y. It's going in the y direction, so the y variable is what gets multiplied. And specifically, it gets multiplied by 2, since that's our dilation factor. So, our coordinate is as follows. We start from xy, and we end at x comma 2y. As an equation, it would look like this. X equals x prime, and y prime equals 2y, right? There's your x prime and y prime. From there, you just rearrange to get the x and y on their own. So instead of having y prime on its own, you're now going to have y on its own. Our function is y equals root x, and so you replace the y with the y over 2, and you replace the x with the x. Rearrange, and your function is now 2 root x. Basically identical when it comes to dilations along the x or from the y. Again, that's just if I go to the handwritten bit, it's as if you were stretching horizontally. And so you could say you're either running alongside the x here, or you could say you are going away from the y-axis. The rules are the same though, we're just applying that dilation factor to the x rather than to the y. So now x prime is ax and y is y. Rearrange, substitute, and then when you substitute this one, this is where you get a bit of an oddity, right? It looks a little bit different to what we saw last time, which was you replace the y with y, so nothing changes there. But when you replace the x with x over a, there's no further need to rearrange. The only reason we rearranged before was because we wanted to have y on its own, right? We didn't want to have, for example, 2y here, or y over 2. That was not great. Yeah, here it is actually, y over 2. That's not how we use functions. We use functions with y on their own. But when it looks like this, that is valid. And so the reason why that's important to highlight is because dilations along the x look like a division of the x, whereas dilations along the y look like a multiplication of the entire function. So two things that are very, very similar look very different when you actually put them into a function, but they perform the same transformation. So again, if we look at how that would apply to the graph of square root x, well, instead of having x comma 2y, we now have 2x comma y. Rearrange, substitute, and just like that, there's no further simplification to be done there. And so you see how you have a division by 2 rather than a multiplication of 2, even though the dilation factor in both circumstances is still considered 2. Okay, that's dilations. Now for reflections. Reflections tend to be on the easier side. We are almost intuitively understanding how reflections work because, well, pretty much everyone that I know has ever seen a mirror, right? You see your reflection in a mirror. And that's pretty much the gist of what's going on here. You imagine that one of your axes is acting like a mirror. So if I just draw up another axis so we can have one that's a little bit less crowded. If you imagine having a point here, there's two ways that you could reflect that point. You could either reflect it across or in the y-axis, in which case it would end up here. I'll call that 2. Or you could reflect it across the x-axis. Usually you say about an axis, in which case it would end up here. Those are the possibilities. Now you could have both at the same time. You could reflect both in the x and then in the y, in which case you get to 4, or you could, reflect in the y and then in the x, in which case you get to, well, still 4. There's something we'll look at in a moment. The fact that there are multiple ways to get from one point to another is kind of one of the bigger issues when it comes to these transformation types of questions. You'll find that there are multiple correct answers. Sorry, multiple correct answers. But okay, How do we identify reflections? Well, we identify reflections by applying a negative sign to the point that is getting shifted over. So if you see our little picture here from 1 to 2, if you imagine the y and x coordinates of both of those points, you would say, well, okay, these 2 points have the same y coordinate. They're horizontal to each other. If this was y equals 2, then that would be y equals 2. But what has changed is the x, right? The x is flipped. And so when we have a reflection in the y-axis, this one being the y-axis, then the x is what gets the negative sign, because it's the thing that's being flipped. So we have our point. X prime is now negative x, and y prime is now y. Rearrange, substitute, and when you do that, you find that any reflections in the y-axis will look like this. You take whatever your function is, and everywhere that you see x, you replace with negative x. That's the shortcut. So that works exceptionally well when you have a function that isn't in a transformed state, or at least not in a state where you can easily identify what each of the factors are. So in this case, the shortcut would be to simply replace every x with negative x. But if we follow the 3-step process, then it would look something similar to this, where x prime is now negative x. Rearrange, every x you now have is being replaced by negative x. So here's the original function. This x gets replaced with a negative x. Just don't forget, that x was squared. And so when you replace the x with negative x, the negative x now has to be squared. But this one doesn't have any such restriction. It's just 3x, and so the x is being replaced with negative x, giving you, well, a final answer of 2x squared minus 3x after you've simplified everything down. Reflection in the x-axis, as you might imagine, is very similar, but the negative sign is now applying to the y. Once again, if you look at the handwritten bit, we have the point 1 to 3. You see that x value, so if this was the coordinate x equals 2, that vertical line represents x equals 2. But what's changing is the y values. So when you reflect in the x, it's the y value that changes. So the y value gets a negative. But otherwise, process is identical. Rearrange for y, sub into f of x. So negative y is replacing the y. And then because we want to have y on its own, when we do these, when we work with functions, that negative sign is going to get flipped over to the other side by multiplication. And so you see that when you have a reflection in the x, the negative sign is applied to the entire function rather than just the x, like in the previous circumstance. And so if we then go ahead and apply that to the same function we had earlier, now there's a negative sign on the y. Multiplying both sides by -1 means this is going to become negative and this is going to become negative. And so when you compare the two things, what you have is both terms negative here, but only one term is negative there. So minor differences. Just by looking at those end results, it would be borderline impossible to tell. We'll look at how to handle that later by doing these things by recognition. But for now, this sort of 3-step process is at the very least the fundamentals of how we handle these. Okay, and then when it comes to translations, this is where you're either adding or subtracting a full term to either the x or the y, depending on what direction you want to go in. So horizontal translations, as you might imagine, means adding or subtracting something to the x variable. If you want to go horizontally, well, our x-axis is horizontal. And so if you had some point over here and you wanted to shift it to the right, well, let's say this was 2 and I wanted to shift it to 3, I would have to add 1 to my x value, and then that would shift it to the right and end at x equals 3. That's what we're doing here. We're adding to that x variable. Now here's where it gets weirder, because you might have seen that horizontal translations mean negative is right and positive is left. This is why. So you start with that initial assumption that if you add something to x, it will move in the right direction, move towards the right. But when you go ahead and rearrange for x and y to go ahead and sub that into our function, that positive now becomes a negative. Right? We started with x prime equals x plus a. To get the x on its own, you subtract a from both sides. So when you go ahead and substitute everything in, y stays the same, but x is now going to get x minus a. So it is still true to say that you do want to add to move to the right direction, move in the right direction rather, but when it appears in a function, it's kind of like the opposite. It appears as a negative. We saw something similar, of course, when it came to the dilation factor, where normally we think of multiplication, it's division. So I guess one way to think about how the x transformations work is that you kind of just think about them as the opposite of what you would normally expect. If you would expect multiplication, it is division for x. If you would expect addition, it is subtraction for x. Bit of an oddity, but at least this hopefully gives you an appreciation as to why it is what it is. Okay, we've had this polynomial before. Let's say we want to apply a horizontal translation of -5 units. So -5 horizontally would just mean 5 to the left in English. So we're going to add -5, or just replace that with a subtraction, since that's how math works. Rearrange in terms of x and y is going to convert that negative back to a positive, and then when we sub that in, we're just going to replace every x that we see with x plus 5. So we've got this x here that is squared, now it's going to be x plus 5 that is squared. We've got this x here that's multiplied by 3, now it's going to be x plus 5, all multiplied by 3. And then usually you're going to have to expand everything out, simplify, and then you get your final quadratic. Depending on what the question is actually asking you, you may not have to go that far. You might have to complete the square on this. That'll be question dependent. Okay, and then lastly is going to be vertical translations. So as you might expect again, when it comes to vertical, that's the y-axis. And so we're going to apply that coefficient. I guess we technically call it a constant in methods. We're going to add or subtract that constant to the y term instead of the x. Okay, same steps as always. Rearrange. You see that that positive now becomes a negative. Again, here is why it doesn't end up staying a negative. Because when you replace the y with the y minus a, you just chuck it back over to the other side, because that's the general form of how we express functions. So in the most technical sense, x actually had it right the entire time. It was the y that was weird. But when you actually rearrange it, well, you get it into a more familiar form. So those are pretty much all the fundamentals there. I have another example of how it works, so I guess we'll just finish up with that. Okay, so in this case we're going vertical translation -2, which just means shifting 2 units down of the same function. Adding a -2 is the same thing as just subtracting 2. Rearrange, make the positive, replace the y with y plus 2, and then chuck it to the other side with a subtraction. That pretty much covers all of the fundamental transformations. These are like the basic transformations that you could ever apply to a function. The tougher part is, how do you apply a sequence of transformations? This is where people tend to get a little bit messed up, because the problem is that the order in which you are given the sequence in matters a lot. And if you're just looking at the rules individually, so if you're just looking at, okay, I have f of x plus a for vertical, or I have x divided by a for dilations along the x. If you're just looking at those, it can be a bit difficult to figure out, well, what order do I do these things in? This is where using a point transformation can be significantly more advantageous. So this is now a 5-step process, but really all we're doing is repeating the first process that we did. In this case, it's going to be 3 times over. Basically, you'll do it enough times to where you go through the entire list. And then only when you've gone through the entire list do you then sub into your function. This is or at least my recommended way of handling these types of questions, where you're trying to apply a sequence that's given to you. So to highlight the difference between the order in which you're given transformations, I've got 2 examples. Both have the exact same transformations in them, but they're done in a different order. And I'm doing this just so I can highlight that if you do things in a different order, you do get a very different result. Okay, so first transformation of this list is a dilation factor of 3 from the x. If we're going away from the x, then it's the y that we're moving along. And so the y is going to get that multiplication because it's dilation. Reflections are negatives. If it's a reflection in the x, then it's the y values that are flipping. So you take the point that you ended off with, and then you use that as your new baseline. So you're now starting at x comma negative 3y, and you're putting a negative sign on that, not the original xy. And then lastly are the translations. So you can do these individually if you like. I've kind of done them both in one go, where it's a translation of 5 in the positive x and 1 in the positive y. So I take my point that I ended up with, or left off with rather, add 5 to the x because it's 5 in the positive x, and add 1 to the y because it's 1 in the positive y. And that is that final sequence. Now we could then rearrange that and sub that into a function, but just to highlight the main thing I want to highlight here is the difference of what the two sequences look like. In example 2, we had translations first. So it was a 5 in the positive x, 1 in the positive y. So you go from your initial point xy up until x plus 5, y plus 1. Now here's where it gets interesting. When you apply a reflection in the x-axis, you're still putting a negative sign on the y, but that's not strictly what you're actually doing. You're putting a negative sign on the y spot. So this whole thing is the y coordinate. You're putting a negative sign on that, not just the thing that says y. It's an important distinction to make there. And that's why when you do things in different orders, specifically around the translation terms, that's where it really starts to become an issue. But okay, same thing works with dilation, right? Dilation of 3 from the x means that you take whatever was in the y spot and you multiply that whole thing by 3, not just the y variable. And even just looking at these terms here, you got negative 3y plus 1, and you got negative 3 bracket y plus 1, which is significantly different, right? If I expand that out, or at least that bottom one out, that would be negative 3y minus 3, whereas the original was negative 3y plus 1. Those two things, by observation, are not the same. Just for fun, I haven't actually read it in my notes, but just for fun, we'll actually apply one of those transformations. So let's go with the example 1. So to actually then apply that to a function, you would have x prime equals x plus 5, and you would have y prime equals negative 3y plus 1. Okay, negative 3y plus, okay. So the next step of the sequence, maybe I'll scroll up so you can see that. So we've currently done up until step 3 by going through that full list. Now we just do our same steps as earlier, which was rearrange to get in terms of x and y. So here's my x, I want that on its own, which means I have to subtract 5 from both sides. X prime minus 5. Similar thing for y prime, I'll do it in 2 steps. First, you would be subtracting 1 from both sides. Okay, I guess we'll do it in 3 steps. Then dividing by 3, so y prime minus 1 all divided by 3 equals negative y. And then finally, multiplying both sides by negative 1 is going to get us, yeah, we'll put it out the front, why not? Negative bracket y take 1 all on 3. Now, I haven't written a function here, so let's just imagine some generic y equals f of x. All it means is, everywhere that we see x, we replace with that. Everywhere we see y, we replace with this. So, first things first, y. Negative bracket y take 1 over 3 equals some function of x take 5. That's pretty much it. Of course, you can then rearrange to get y on its own if you want it to look like a function, which would just be a matter of multiplying both sides by 3. Negative bracket y take 1 equals 3 f of x take 5. Multiply both sides by negative 1, negative 3 f of x take 5. And then finally adding 1 to both sides. Negative 3 bracket f of x take 5, and then a plus 1 at the end. Yeah, and so you can imagine whatever f of x is, you're just going to replace every x with that, and then the y will look pretty much identical to what we just did there. Okay, that's sequences of transformations. If you're already in the school group, then you'll have access to this in the transformation spot. There's a nice little summary here as to the processes that you follow to apply them, or if you want to also start getting used to, which you will have to, start getting used to all the shortcuts as to what those functions are or what they look like immediately, so you can identify them by recognition. Okay. We can then follow up with probably one of the hardest topics in transformations, which is kind of doing the reverse of what we just did, where instead of applying a sequence of transformations, we're now trying to determine what the sequence of transformations must have been just by looking at our function. Now, this is where doing things by recognition can be helpful, because if you can just identify, okay, I see a dilation there, a translation there, it must have been X and Y, whatever those are. But the point notation thing also works, and it works for everything. No matter how complicated it is, you're going to follow the same steps. Again, when there's multiple terms in there, putting them in the correct order is important. It's very important. So primarily we're going to focus on the first method because you don't have to think at all that hard as long as you're just following the steps. Whereas if you're doing things by recognition, you have to think about all the, what would there be, about 6 different rules for how they work, because there's 6 different transformations. I think I counted that right. Anyway, the process that we follow isn't super difficult because it is just going to be the reverse of what we did in the application of transformations. So let's see. It's a 4-step thing. We start by identifying what our original function is and what the new function is going to be. So basically, where are we starting and where are we going? We're trying to get everything that affects the y on the y side, everything that affects the x on the x side. That'll make it easier to figure out what transformations are affecting what. We then use our point conversion to equate where we're going and where we started. Rearrange for x prime and y prime this time because we're going backwards, right? We're trying to get back to that initial stage. And this step 4 may or may not be optional. If you finish up with step 3b, then you'll have your answer in point form. If you go all the way to question 4 or step 4, it would be putting it in English, right? Like actually writing out what those transformations are in the correct sequence. I have a few examples here. One that is going from a transformed function to an untransformed function, and one that's going the other way around. Now, I have both of those examples in there, not because they are different, but because they are the same. And I want you to understand that you don't have to do anything differently. You always follow the same process. Doesn't matter what the functions look like. It'll work no matter what. So, a typical question might look something like this. In this case, we're going from a transformed truncus, right? It's got all these translation and dilation factors in there, to an untransformed one. And we're trying to figure out what would it take to go from this f of x to g of x. Just going to take a sip real quick. Okay. One thing we can do to help us out a little bit is use different notation for the different functions. F and g is all well and good, but it can still be a bit hard to figure out which one's which. So we're going to use x and y to denote the function that we're starting with, and we're going to use x prime and y prime to denote the function that we are ending with. Okay, so we're told that we're going from f to g. F is what we start with, so it's going to stay as just x and y. G is what we're ending with, so it's going to get y prime and x prime instead. So it just means that instead of saying g, I say y prime. Instead of saying x, I say x prime. From there, we just want to identify what transformation factors are affecting y and which ones are affecting x. This is where having this sort of cheat sheet can be helpful, because if you can identify, okay, this is affecting y, this is affecting y, and this is affecting y, then this will make this step a lot easier. In fact, it's actually required, pretty much. So if you want to get everything that affects the y onto the y side, that's going to be this plus 6, which is a vertical translation, and it's going to be this dilation factor of 3 along the y, or from the x. To rearrange, it would just be a matter of subtracting 6 from both sides and dividing by 3. Currently, we've now got everything that affects the y on the y side, so you can imagine the translation and the dilation, and you've got everything affecting the x on the other side, or you could call it the x side if you like. in which case we're just seeing a translation of 1 to the right. You would also do that for the other function, if applicable. So if both of them were transformed, then you would also have to do that for the other function. In this case, it's a bare bones truncus. There's nothing to rearrange, so we just leave it as is. From there, we're going to write our conversion, which all that means is that we look at the x components of each function and say the x component of the first is equal to the x component of the second, right? This is a transformation. It's going from one to the other. And we do the exact same thing for the y components. So when we do that, we say, okay, here's the y component of f of x. Here's the y component of g of x. Those two things are equivalent. Exact same thing for x. Here's the x component of f. Here's the x component of g. Equate those two things together. Now, if you really want to, you can take the entire right-hand side. That will still work, and you can still do enough rearranging to solve to get x on, or to get x prime on its own. But really, we only care about the actual transformation that's applied to it. So, again, to reiterate, you don't need the entire thing, but it's not strictly wrong to take the entire thing. It'll just take a bit longer. So if you forget that, if you're ever in doubt, just take the whole thing. But you won't be in doubt because you'll have practiced this a bunch of times, right? Okay, so rearranging for x prime, y prime. Again, that's a bit different to the previous example because we were applying. We're doing everything in reverse. So we're going back to x prime, y prime. Good news is, when you have an example like this, it's already in x prime, y prime. So there's no actual step to be done here, although that will be applicable in the next example. So as an expression, that means our new x is equal to that. So x goes to the new x, which is x minus 1. And the new y is equal to that. So y prime is equal to that. Now that might be okay for some questions. If they ask it for point form, that's a valid answer. But if they want it in English, then you're just going to have to go through this next step, which is, okay, so this is where it gets a bit on the trickier side, because there are a lot of different ways you could express this. There are two main methods you can go about it. You could do dilations, reflections, translations in that order, or you can flip the order, which is what I kind of recommend, and do it using this sequence, which is we start by rearranging to get rid of the coefficients off of the x and the y. X is already fine, there is no coefficients there, but y has this division of 3 applied to the entire thing, and so we're just going to bring that out the front. That doesn't technically do anything, but it does make it a bit easier to see what's happened. If you have done it in that order, then you would do translations, reflections, dilations. So you go through, you look at each of these equations for both x and y, which are independent, and you say, well, okay, translations, what have I got? Well, I've got a translation of 1 in the negative direction of the x, because it's x minus 1. We've also got a translation of 6 in the negative y. So again, translation, translation. Reflections, do we have any? No, there are no negative signs applied to the x or the y, so there are no reflections. And then lastly, dilations. We see a dilation factor of 1/3 along the y. You can say from the x if you like, that's fine. So that's one valid sequence of the transformation. Now, even doing the exact same steps here, you can still do it a little bit differently, because one of the key things you need to be aware of is that the x and y are independent. You can do them, well, one x and then the y, or we can intermingle them like we did here. In this case it was, well, I guess not really intermingled, but we did translations and dilations. You can do everything in the y and then everything in the x next, right? The only thing you have to be aware of is doing them in the order translation, reflection, dilation, in the x and then in the y, or y then x. Just make sure they're separate. So one alternative way is to say, okay, I'm going to do the y stuff first, which means 6 in the negative y, dilation factor of 1/3 along the y, and then only then do I go back to grab the x. So very, very minor change there. Both of those are correct answers. This is the challenge of this topic, because the book will only give you one possibility. The book typically does DRT. So it typically goes dilation, reflection, translation. How do you handle that? Well, instead of doing a factorized approach, which is what I've just done here, you do an expanded approach, which just means you go through. The only thing that needs expanding is this y minus 6 over 3. So you would take your y minus 6 over 3, and you would just apply that division of 3 to both terms, but like really make it explicit. So you now have y over 3 minus 2. Now you can do DRT, where an equivalent would be dilation of the third, let's just say from x. Then it would be, so dr, there's no r's, and finally the t's. So there's a translation of 2 down, and there's a translation, the x side was already fine, so that was 1 left. So already you're seeing 3 different ways that you could do the exact same thing. All 3 of those answers are correct. So my recommendation is just pick something that works for you, right? Just do one thing over and over again and be good at doing it that way. Once you've achieved that, once you've got that consistent, then you can start worrying about other ways of representing them. The reason why you would have to start worrying about other ways is because the typical, well, atypical exam question will say, hey, here's 1, 2, and 3. Here's the list of transformations you need to give me, but I'm only going to tell you that 1 was done. You got to figure out what the other 2 in the sequence are. And so that might force you to start with a dilation or force you to start with a translation. And so by understanding how to do both, you'll get that mark, as opposed to, well, being sad because you didn't learn both ways. Okay, so it's a lengthy process. Same thing, untransformed to transformed. It just means we're starting with an untransformed function, x squared, nothing to it, and we're going to a transformed version of it. Once again, x and y goes to the original, x prime and y prime goes to the new. The new is g, and so g gets y prime and x prime. From there, get the x stuff on the x side, the y stuff on the y side. This one's already fine, f is fine. G, however, needs to have the 3 to the left side and the 2 divided. So you subtract 3, divide by 2, and then you're golden. Once again, look at the x and y components of each other. So here's the y component, there's the y component of the first, y component of the second, equate them. X component of the first, x component of the second, equate them. Get x prime and y prime on their own, and you get your expression. Now, this is where you get to the situation where you can do basically whatever order is. So there's multiple correct answers, not all of them, but not infinite correct answers. There's definitely more things you can do wrong than right. So again, pick one way that works for you. I recommend doing the factorized approach, just because that's kind of what you already do when you do functions. Like, you typically always start with your function and get it into a transform state, so you can more easily see what those transformation factors are. So at least that way you're doing the same skills. But okay, x plus 2, nothing needs to be done there. This bit, however, has a multiplication of 2 on the y, so we're just going to take that out the front. And then we do TRD. So translation of 3 over 2 in the positive y, that's this one. Dilation of 2 along the y, so I've chosen to do both y and then go back to the x in this case. And then, yeah, translation of 2 to the right, because it's a plus 2 on the x. That's the gist of how that works. This I recommend for the tougher ones. When you start seeing like a whole bunch of transformations all in the same thing, it can be difficult to figure out what the order is if you're doing it by recognition. What does by recognition mean? Well, that's what this stage of the lecture is going to be about, as I grab another sip. Okay, so how do we do things by recognition? It literally just means I am looking at both of those functions and I'm seeing, okay, I know that's a translation to the right by 2. That's what recognition means. Now, how do you actually achieve that? Well, we basically follow these 3 steps. First, we just got to figure out, or make sure, that both of our functions are in their general form, which just means a form where you can easily identify what each of those transformations are. What did I say here? Remember that y transformations are independent to x. Yeah, okay. So that's just there to remind you, hey, don't get hung up too much about the order of things. If you can identify which ones are y's and which ones are x's, you can do all the y's first and then all the x's. That might make it a bit easier if you're doing a recognition approach. And under these circumstances, DRT tends to be your friend. So we'll do that order instead. So we have a nastier looking example here. We've got one turning point form quadratic and one that is in the polynomial form of the quadratic. And we're trying to say, okay, how do we get from f to g? Just by looking at it, that's going to be impossible, right? It's very, very hard to, like, even if you try to follow the earlier process, where you try to get all the x on the x side, the y on the y side, if you're looking at that, you're thinking, I've got no idea what to do with it. So the recommendation is to complete the square. And so all I'm doing here is completing the square on g of x so that it becomes a turning point form. Now when you compare the two things together, you can see, well, okay, I got this thing, I got this thing. I can see this one has a horizontal translation of 2 to the right. This one has a horizontal translation of 1 to the right. This one's vertical 7, this one's vertical 12. This one's dilation 3, this one's dilation 4, along the y or from the x. Okay, so DRT. The reason why I recommend doing DRT under these circumstances is because dilations impact the translations. If you saw from earlier here, when we had the translation first and then dilation, the dilation turned that +1 into a 3 instead. And so if you do the dilations first, then you get into a situation where you don't have to worry about what the translation needs to be after that. There's no multiplication factor to keep track of. So, first things first, dilations. What would it take to get from, okay, let's see my notes. F had a dilation of 3. Okay, so we're trying to go from 3 to 4. What do I, oh, sorry, it's from 3 to 4 here. What would it take to multiply 3 to make it equal to 4? Well, you multiply by 4 over 3. And so that's going to be your dilation factor. You apply a dilation factor of 4/3 along the y, which means you take the original f of x, you multiply the entire thing by 4 over 3. You'll see that the 3's cancel out and you get left with a 4. What happens is that translation factor that was a 7 is now a fraction. Now that's not bad yet. That's not our answer. It's better to have it done earlier than done later. I'll put it that way. Okay, any reflections? Well, if we compare the new forms of f and g, you can see there's no negatives on either the x or on the entire function. Or at least if there are, they are invisible because they were cancelled out. And so we can ignore the opportunity of reflections. And then lastly, translations. So, what would it take? Okay, which one did I say first? We did verticals first. Okay, so if we're trying to go from f to g, then it means that we need to get from 28 over 3 down to 12. What would it take to do that? Well, we just got to figure out, right? We're just going to find the difference between those two things. So what is the gap between them? And in this case, it's 8 over 3. So if you want to go from 28 over 3 to 12, you need to add 8 over 3. So you need to go up vertically. And so you do that. Yeah, it simplifies to 36 over 3, which, well, duh, is 12. We did that on purpose for that very reason. And the last thing to fix would be the horizontal translation. So we see that we are, where is it? Here. So we're going from x minus 2 to x minus 1. So that means that we are going from shifting right to the 2 in the direction of the positive x, to 1 in the positive x. Which means, if you look at that graphically, this one here is x equals 2, and we're trying to get here to x equals 1. What would it take to do that? Well, go 1 in the left, which in function land means that you add 1 to the x. And so, mathematically speak, or at least transformation-wise, you are shifting to the left by 1. And so to summarize the 3 things that we had to do, it was multiply by 4/3 to get that dilation factor correct, then apply a translation vertically of 8/3 to make it equal to that plus 12, and then 1 to the left to get the x minus 2 down to x minus 1. That's how you do things by recognition. This was a hard recognition one. The gist of it is it's more applicable for like this sort of stuff here, where it's like, okay, what would it take to go from F to G? You can immediately see it's just going to be a shift to the right by 2. Again, still works for the more complicated stuff. Bit harder. I guess just sort of pick your poison. Which one would you rather do? Would you rather work with all this algebra and sort of pick and choose what factors you're multiplying by? Or would you rather stick with the point form because you'll have to do that anyway for some of these? Up to you. Alright, that about does it for me. No one else has joined yet, so I think I'll just leave it here and call it a bit early. Alright, enjoy.